Yo, yo, what's up? Today we're working on my operating system that I'm writing for fun on stream. It's written in Rust. Right now it doesn't really do much. It's an x86 operating system that is currently loaded with QEMU. And what it can do right now is it can like print to... Here, let's see. Sorry, shouldn't have closed that. It can print to like this like VGA output buffer, which is like the same thing that you would like plug your monitor into. You can see we can like get the current date. We can initialize some memory and like create like hash maps and vectors and stuff because we have like an allocator implementation and Rust gives us a bunch of that stuff for free. And then we have a way to exit, which isn't working right there because I disabled it. But if I like run unit tests, then at the end this like cleanly exits and it will like tell us if we the operating system will like flag to the host system here if the test failed, etc., etc. Today what I want to work on is like a continuation of what we were working on yesterday, which is interrupt handling in ROS. So yesterday we got to the point where we set up these like interrupt handlers and like a registration mechanism for drivers to register interrupts with the interrupt controller, I guess. So when like the CPU gets an external interrupt from like something like the RTC clock driver or like IO or something, we can like register a handler for that. And what we see here is if I run cargo run, we do in fact get an interrupt here. We see like hello from interrupt 0, which is what we wrote here. But what we don't get is we're supposed to get these like periodically, right? The RTC is supposed to say like, hey, we got another one. Hey, we got another one. Hey, we got another one. And that's currently not working correctly. And so what I wanted to look into today is how do we fix that? And maybe once we figure out how that's supposed to work, we can kind of like write something that's a little bit more sane, I guess. Because right now we're just kind of like handing stuff, we're just writing this in main. So we'll do some like proper setup where like the driver registers and the driver owns the state of whatever the interrupt is supposed to do. And maybe we'll handle like, maybe the interrupt isn't supposed to be heavy. Maybe the interrupt's supposed to be like something that happens pretty quickly. And maybe we should be like maybe we should have like an interrupt handling thing that happens in the main loop that's like flagged to from interrupts. I'm not really sure. So that's what we're going to look in today. So today's goals, RTC driver should be like, we should have periodic polling of the RTC driver. And maybe if we get to like a nice place here, maybe we should have some form of like sleep function that halts the CPU and can like update based off of the interrupt that's happening from the RTC. And maybe we can find a way to like cleanly set up like ownership of like system time and a way to like track that down, etc. So let's just jump in. I did some experimentation yesterday. And I think what I was missing was OSDev wiki pick. So there's two things here. One thing we need to coordinate with is the interrupt controller itself. So outside the CPU, there's like this interrupt controller called pick. I wonder what pick stands for. Programmable interrupt controller. Nice. And we have our like clock here. RTC, which is just like a rock that's oscillating with electricity, you know, a little crystal in there. He has like an IRQ line that goes here. And what we're supposed to do is, there's also some like IO ports going directly from here to here. I guess more like here to CMOS to RTC or something. And so there's like two things we have to coordinate here. One is we need to coordinate between these two people. We have to like this, if the interrupt controller triggers something, he needs to say to this, the CPU needs to tell him like, hey, don't worry, we've handled that. So like if you get another one, we're good to go. And we also have to like let the RTC know that we've handled the interrupt. Both of these guys need to like be aware that they're allowed to send something else. Because if you like look at like a timeline of like what happens here, if this is like the interrupt line going from the pick to the CPU, I think it's something like, how do I say this? I think that like we have like interrupt goes high and This is like IRQ. And I think essentially this is when we get like an interrupt in the CPU on like this edge here. But until we say to the pick, like, hey, we're done. So we're like, it will like stay in this state. So we have to tell it to go back down so that this edge trigger can happen again. And I think it's the same thing with the RTC. And there's like another piece that I haven't really communicated in here is that there's actually two interrupt controllers like in series with each other. And they're hooked up like this. So this goes to this guy, this goes to this guy. And so we actually need to do the same thing where all interrupts from pick 2 go into like one specific interrupt of pick 1. So we actually need to tell both pick 1 and pick 2 that we've handled the interrupt and the RTC. So we need to talk to all three of these. And I think this is actually like this too. So we have a direct line from the CPU to pick 2, direct line from CPU to pick, and a line from the CPU to the CMOS, which connects to the RTC. And so we have to say 1, 2, 3. We need to flag all three of those that we're ready to go, I think. So let's try that. For now, we'll do this all in the interrupt handler. So here I'm like getting IO ports from my like port manager, which is in theory, it's supposed to make sure that only one person is like writing to a given port. The idea is that like in my RTC driver, you might have like a sequence of events that you need to write to one port. And if you allow multiple people to use the same port nums, they could like clash with each other and like things could go wrong. So there's a port manager. He says like, hey, nobody's using this port. You can use it. Now, what I'm actually doing here is I'm lying. And I've constructed a new port manager specifically with the intent of allowing multiple connections here because I'm just trying to like debug. So then I have to write to both these, the pick 1 and pick 2. I need to say end of interrupt, I think is 0x20. Let's just double check that. Where is it? Somewhere in here. They say end of interrupt. Yeah, here we go. End of interrupt. The most common command issued to the pick is the end of interrupt command. This is issued to the pick chips at the end of an IRQ-based interrupt routine. If the IRQ came from the master pick, it is sufficient to issue this command only to the master pick. However, if the IRQ came from the slave pick, it's necessary to issue the command to both pick chips. Okay, so here we know that we're in pick 2, so we'll just issue it to both. And then the other port we need is the RTC. And what we need to do here is we need to use this, hold on, where does it say? Interrupts and register C. It is important to know that upon an IRQ8, status register C will contain a bit mask telling which interrupt happened. The RTC is capable of producing a periodic interrupt, an update ended interrupt, and an alarm interrupt. If you are only using the RTC as a simple timer, this is not important. What is important is that if register C is not read, an interrupt will not happen again. So we just have to read register C, which is done with these two commands. And our code looks a little different here. So their output B is our command, our like ports.write B. So we need to allocate these ports. So we'll say CMOS command is port manager request port 670. And this is CMOS, not CMOS. CMOS data is 71. And here we can say pick 1, or sorry, not pick 1, CMOS command write B this, and CMOS data read B. And this probably should come before this. And I think now this should work. So let's try cargo run. There we go. Okay, so that's a really good sign. So that means now that our interrupts are now happening back to back to back. So it means that we understand this correctly. And now all we need to do is figure out like what the piping of this looks like. So really, I would argue that interaction with the RTC should be handled by the RTC driver. That makes sense. But interaction with the interrupt controller should probably be owned by like the interrupt controller, we'll call it. So let's take a little look at that. So this guy here, he's the one who owns these PIC registers. And the problem here is we need to say within our interrupt that we have handled what we need to, but we need a way to like pass these ports over. So let's just think about that. So these interrupt handlers are run in the context of the CPU just kind of like jumps to them. And so there's no like state associated with them. If we want any state, we have to store that in like static memory in a way that is safe. And I do kind of want to keep using this like port registration mechanism to make sure that we're not clobbering. So maybe what we'll do, let's think about this. Let's think. I guess somewhere we're going to have to stick these ports into static memory, right? So let's kind of just like stick them all together. Pick ports, we'll call it. And we'll say pick one command is a port. And this is pick one data. Pick two command, pick two data. And on initialization, we'll stick these somewhere. So let's see, we don't really have in static memory right now, we have an interrupt table, which is the locations where the CPU is going to look up where to jump. And this interrupt handler, which is, I believe, already accessed in our interrupt handler days. So, maybe we'll, instead of calling this interrupt handlers, we'll rename this to interrupt handler data. And we'll have handlers, but we'll also have ports. And in here, where did I write those pick ports? Pick ports. Sorry, I keep getting lost. So this absolute shit show of code here is a result of having to register every interrupt for each interrupt vector. Sorry, every interrupt that could happen, I want it to go to my interrupt handler, and so I just have to register them all manually for now. I'm sure there's a way to do this better. In fact, I've been like Googling about this a little bit, but for now, there's just this like shit show of code that I have to scroll through sometimes. Anyways, we have these ports, and we can store them here, but the problem is that these guys won't be static. So maybe these should be like option pick ports. And right now, the synchronization primitive I've been using to like work with these is I say interrupt guarded, which says like disable interrupts while you're interacting with these. But I do think that that's actually wrong now that I think about it, because disabling interrupts will cause other interrupts to fail. And so what I really want is like something where I know that they're not going to be like in an inconsistent state during when an interrupt occurs, and these can't really be. Because, well, I guess they could. Well, no, they could be, because they run like some amount of. Let me think. I think they can't be, because all they're doing is like, if I interrupt on any instruction in this like write B, it's gonna be like, it's not gonna like be unsafe for another thread to use them. But I guess we do need to make sure that we're the only mutable reference to these, just for like Rust rules. So maybe I'll keep this for now, but I would like to think about if there's a way to like do some form of like thread local or something. But for now, we'll kind of just work with this. So here, our ports are interrupt guarded, new, none, right? Because we haven't initialized these yet. And then here, we just have to initialize ports. So say ports lock equals some port, like this. And it doesn't like that for some reason. Invalid left-hand side of assignment, probably because I didn't semicolon, right? Cool. And now in here, I just need to provide the pick ports. So pick ports, let ports is these guys without the mutes. And presumably somewhere here, I can pass it into initialization ports. Okay, so now in my generic interrupt, first let's rename this guy to interrupt handler data. Here, I can say that when my handler is complete, we can say if interrupt number is greater than or equal to pick one offset, which is like the interrupt number associated with interrupts coming in from from the first pick control or interrupt controller, and we're less than pick one offset plus 8 because there's 8 possible interrupts. I think this shouldn't be less than or equal to. I think that should be less than. Oh, and that's kind of cool. I've never seen this before. That's a kind of cool little lint there. So let's say if pick one offset plus 8 contains interrupt number. I've never seen that. That's cool. Then, is that actually just as fast? That seems... Oh, neat. Okay. Okay. So if this contains the interrupt number, then we have to reset pick 1. And we have to do the same thing with pick 2. But if it's pick 2, then we need to reset 1 as well. So we'll say let ports equals interrupt handler data ports lock, and ports.pick2 data, we need to write, I think it was 0x20 for end of interrupt. And probably we should define that as a constant. So const end of interrupt equals 0x20. Okay. So this should be end of interrupt. Interrupt. And here we need to do this like as ref expect thing again. So we say like this, because we had to initialize our static had to be at compile time. We needed to put an option in there as like, yes, it's here or no, it's not, because we can't like get the ports at compile time, but at compile time, we need to like put something in there. And so here we're saying like when we initialize, we'll pass the ports in, and that's when these will be valid. And so now we can just say like, crash the kernel if this is not initialized, because like somebody who's coded this, i.e. me, has done this in the wrong order. So let's drop in a interrupt handlers not initialized here. And here we need to flag end of interrupt as a U8. And this needs to be mutable, or else Rust gets angry at me. What doesn't it like? as mute, I guess, here. And it doesn't like, we have to do some like jiggling of stuff to make sure that Rust gets lifetimes correctly, which is annoying, but what you gonna do? What you gonna do? There we go. Okay, and then we need to do pick one as well. And then we do the same thing down here, but only for pick one. Cool. So now, if we go back to main, we should be able to delete some of these hacks. So here we can delete anything related to handling of like interrupt controller state. And if I run this, hopefully, okay, no handler for interrupt 64. So we fucked something up big time. Oops. Oops, oops, oops. How did we manage to fuck that up? Cargo or git diff. What did we change? Because nothing about like interrupt 64 should change here at all. Unless, oh, oops. I see. Generic interrupt handler. I made a mistake here. So here I was writing to pick to data, and I think I actually have to write to pick to command. The end of interrupt is a command, not data. If I write to data, I'm actually unmasking different interrupts, which is a big, big no-no. So let's try that. Cargo run. Oh no, did my PC crash? No? Oh, are we back? We're back. Okay, we're back. Whew. That was scary. So it looks like this is working. So we're correctly resetting interrupt controller state, and we're doing this like somewhat generically. So pretty okay with that. And now, well, let's make a quick little git commit. We'll say that this is a intermediate commit, and we're calling this picks cleaned up in interrupt controller. And we actually accidentally, well, not accidentally, accomplished something that I wanted to accomplish today, which was this guy. And so we'll put this guy here and say that we're working on this now. Okay, so we need to set up interrupts in the RTC driver correctly now. So here, instead of registering manually here, let's go into my RTC driver. And here, he should take in the interrupt handlers, like this. And this guy should move into RTC driver init. So I guess somewhere like, hey, just joining. Can you briefly talk about what I'm doing? Yeah, sure. So building an operating system from scratch in Rust for fun. Today we're looking at interrupt controllers. So let's see if I have this open. When we're running some code, we'll be like, you know, assume it like this is the CPU, he's like here, he's like running some code that's here, and he's like over here, he's over here, and maybe like somewhere externally, hardware might like say, oh no, CPU, you have to do something right now. And so what'll happen is I'll like jump over to like this other section of code over here, it's like the interrupt handler, so I might just like come from here, jump back here, and then jump back over here when I'm done. Say like, oh, yeah, I'll like do this thing right now, even though I wasn't like planning on it. Like not like threading, not like that. Just like, oh, I'm gonna go do this exact thing right now. And so there are like lots of external hardware pieces that might want to trigger this. What we're working on right now is like the clock driver. So every n time, it's just like spinning in a circle, and then when it hits the top of the circle, he goes like, oh, CPU, like quick, update a number. And the idea is that like maybe I can have like some sort of like consistent version of time throughout the whole OS. And what we're doing right now is we're trying to figure out like how can we get the code to like keep track of time that's associated with the RTC driver, the clock. How can we like separate that piece of code out nicely so that the interrupt controller can handle interrupts and the RTC driver can handle like RTC driver stuff. Yeah, high level, that's what we're working on. What we were just working on is that we have these like interrupt controllers that we have to control. So we've kind of like handled that. And now we have this like RTC that we have to deal with. So when I run my OS, oops, sorry, we're in an inconsistent state because I just deleted a bunch of code. One sec. Let's go back a little bit. What we're seeing here is when I'm like running a virtual machine and it's printing out to like a serial console that's like being read back from my terminal. And what we're seeing here is like we do our initial setup, and we're seeing that we are in fact like triggering this interrupt over and over again. We're seeing like log spam of like, hey, the interrupt happened, which means that like what we're doing is working as expected. And so now what we want to do is we want to like pass in this interrupt handler stuff into the RTC driver so that he can register his handler function. So let's figure out here, we'll pass in interrupt handlers, interrupt handler data, I think is what I called it here. We will import this from interrupt handler data. And here, let's just cut and paste this function into here for now. And see what it looks like. So what we can do here is, right, we're trying to remove this last hack. So this last hack is that we're, the bus that we're talking to has like ports on it. So every IO interaction, we say like, hey, let's talk to device at register or at port like 55. And we want to make sure that only one driver owns communication with that port to avoid like multiple drivers clobbering each other. So we have this like port manager that says, hey, I'm going to talk to that specific port. And, or sorry, what I like request a port from the port manager and nobody else can get it. So right now I'm just like constructing a second one that like doesn't know about the first one. And so like I am in fact clobbering that state, which could cause problems. And so what I want to do here is I want to make sure that these ports that are used in the RTC driver are also propagated into the interrupt handler. And I think I can do that by just kind of like moving these out. So I can say like ports, struct ports, and I'll move this guy out of here. And I'll hide him behind like a arc, what do I call this? Arc, something that has like mutability, so interrupt guarded, to say like, hey, we're allowed to mutate this from, this is like basically our like version of a mutex right now. And we put this in ports. Cool, so we need to import out arc, which I think is in the alloc crate. Sync probably arc, yep. And then we need to update all of this code to use these guys correctly. So let's just quickly disable this temp for a bit and fix all the compile errors. So anybody that's currently taking in control and data port, this guy can take in ports directly now, which is this guy. So this is ports. I think this is like this. Then this guy needs to be this, and this guy needs to be the data port. We need to borrow here. Cool. This guy can also take in ports now by reference like this. And we just need to adjust some names here. So this is ports dot control port, and this is ports dot data port. And here, this guy still only takes control ports, that's fine. And this guy takes control and data, so we'll pass in ports and mute ports. And here we'll pass in the control port by reference. So this is mute ports control port, and this is ports data port. Oh, this doesn't need to be by mutable reference. That's cool. And one more. This guy also is ports. Ports. This guy takes in ports. This guy takes in ports now. And we're chilling. This guy now has to take in ports instead of each individual one, and he can pass him on to all of these guys like this. Easy peasy. And this guy should also take him in like this. One more. Okay, almost there. So here we need to actually construct the ports. So here we have struct ports, or oops, let ports equals ports, and we take these guys, stick them in here, which means that he can now come in, be passed in like this, and this guy can also use them. Ports, easy. Need to borrow. I get it, Rust. You like your strong guarantees. Okay. Almost there. This guy also needs to pass in self ports and take in ports. And all of these are going to look the same where they say ports. We're close. We're close. Arguments of this function are incorrect. Expected mutable reference, found mutable reference of type arc. Oh, right. So when we're in here, this actually has to be, we wanted it to be a shared reference to mutable data. So we have arc, new, interrupt, guarded, new ports like this. And then here we have to actually lock it. And probably take a reference like this. There we go. Okay, one more spot. Ports and control port, and we just say C, change two words to ports like this. And now I can just redo that action. Okay. Mute self ports lock. Okay, that's got to be all of them. Yep, that's pretty much all of them. Okay, cargo check. We're close. It doesn't like that I'm using the interrupt handlers because it's borrowing port manager. That shouldn't be true. So here, my interrupts in it takes in a mute port manager, but it doesn't like hold onto it. So probably Rust is getting confused about the lifetimes here. It's seeing like a reference here and a reference here and assuming that they have to be related. But they're not. So I think I can just tell it this reference is a reference to some like static memory. Cargo check. And that does fix it. So that was a good lucky guess. Okay. So we're back in the RTC driver and we're trying to fix this interrupt handler. So let's say this guy has to take a copy of ports. So probably here we need to do this like reference wrapping stuff here. So we'll say ports is arc new interrupt guarded new ports up here. Then in here we can say can do this thing where we wrap this guy in another set of curly braces to do copying of names. And we can say let ports equals arc clone ports. We can now move ports into the closure, so this will be stored in the context that's the interrupt handler is using. And then we can say this is basically read CMOS register ports lock. NMI enable and register is 0x0c. Okay. I think we're pretty much good. Let's just put this guy up here. He doesn't need to be there. So this lock goes away now because he's not in mutex guarded anymore. And this guy needs to go away. Okay. Are we close? Cargo check. Close. This interrupts now is no longer at the top level, so we need to say that this is like a module in our crate. And we're working. So now if we run, solid. We've kind of like hooked everything up so that the RTC driver owns resetting the RTC. This interrupt handler is actually like pretty straightforward. He's doing nothing right now. He is just saying read to the CMOS reg. And I'm pretty sure if we disable this, oh, maybe we don't need to do that. That's interesting. So I thought that when I was reading the RTC driver, I thought that it said that if we don't, or the RTC wiki, it was saying that if we don't read register C, then the interrupt will not happen again. So I wonder why this is still working. I won't worry about it for now. Okay. So let's still just follow that because they want us to. I don't want to just like blindly. Well, I guess I'm of the opinion that I shouldn't do things unless I understand why. And so here, reading this without seeing the behavior where I have to, that's confusing to me. So even if I don't, let's print out what we're getting here. So here we can say format this as like a hex number. And every time it's 0x0, which is interesting because this is saying that it's a mask of which interrupt happened. So is there a data sheet that will like tell me what is supposed to happen here? A typical OS will use this blah blah blah, CMOS RAM, RTC is capable, blah blah blah. Where is like the RTC data sheet? RTC data sheet. Because theoretically, someone should tell me. I wonder if we are in fact using the DS1307. I think that just Googling RTC is probably like not reasonable. But let's see if this gives me what I think I should. So if I look up skim these to try to find register definitions. Data transfer on 2-wire. Yeah, I'm not really convinced that this is what I want. X86 RTC part number. Okay, maybe the Linux kernel will tell us. Linux talk about real-time clock. That usually means something that tracks on the clock, blah, blah, blah. Old PC AT compatible driver. All PCs have a real-time clock built into them. They are built with the chipset of the computer. Some may have a Motorola, blah, blah, blah. This is a clock helps keep. AC Pi is a standard, blah, blah, blah. Interesting. So maybe there's like an RTC interface or something. Let's look up QEMU RTC implementation, maybe. There's a dash RTC, so QEMU system i386 help, and let's see if he has RTC anywhere in here. All right, that's not really helpful. Maybe like Intel's manual will have something about it. Maybe it's like, I would imagine that it's not integrated into the CPU itself, but it's integrated into like the motherboard. But let's see if there's anything about RTC in here. Oh, when I search RTC, I'm getting vert. Okay, so nothing here. Setup reference, like none of these. All right. I wonder like where this comes from. AT model was first in the IBM PC family. Check quick, keep track of time. AT RTC datasheet. Huh. Yeah, I don't know. All right. Well, I guess for now we'll just trust this, and maybe the fact that the RTC is just continuing anyways is like maybe a QEMU oddity. And for now, let's just drop a comment on here that says, or maybe I haven't, maybe the type of interrupt I'm receiving right now isn't one of the ones that would be masked. That's actually what I wanted to find out. Is like, what the hell are the types of interrupts? Alarms, RTC alarm. Like somewhere, somebody somewhere has to know. Like, and I don't like the idea that there's got to be just like a source of truth. Accessing the CMOS chip, real-time clock, CMOS reference, using the like, why are none of these external links like the the source of truth? I just want the source of truth. Okay, whatever. We'll just say clear interrupt mask on RTC. Okay. So we set up interrupts, we clear pick 1, pick 2 RTC. This is done generically, and we handle ownership. I'm like pretty happy with the state ownership here. So we'll call it done. And let's now set up like system time. So here, the RTC should have like this concept of time in him, I guess. And so when I say like read from the RTC, that's like get the date time right now. And I wonder if I just like increment a monotonic clock here, if that will give me something interesting. So let's take a quick look at hold on. Let's throw in a here. We can put like a tick, and this can be like an arc atomic U size, which technically doesn't have to be atomic for now, but I'll allow it. And or maybe actually what I want to do is like an unsafe cell U size. And here I don't need like an arc, I can use like an RC. The reason I'm saying this is because I don't actually need multi-threaded behavior here, because I only have one thread. But probably when I try to pass this to the interrupt controller, it won't let it. So maybe I will just use atomics for now. And also in the future, that will be like future proof of thread implementations. That's fine, I guess. This won't be, I guess. Whatever. This is easy enough for now, and I'm not really worried about like the performance of atomic instructions and stuff like that. So let's just try that. So here, we say our current tick is atomic U size new 0. We'll initialize it to 0. And here we also need this to be in a shared pointer, arc new. Here we can say let tick equals arc clone tick. And here we can say tick dot fetch add 1, and the ordering can be relaxed because we don't really care here. We just care that like they get incremented. I guess it depends on like how strict we want the timing of our clock to be, but for now let's just say we don't really care. Pass this in here, and we can say pub function get tick, and t returns just the U size. And here we'll say self dot, what do we call him? Tick? Yeah, I think we just do this. Can I just dereference him like this? Found atomic use size, so I need to load this as ordering relaxed. Get tick is never used. Okay. So now let's just say we'll log the tick here every time. So here we can say current monotonic time is this, which is RTC get tick. And does this compile and run? Okay. 1 Mississippi, 2 Mississippi, 3 Mississippi, 4 Mississippi. So this is kind of happening about like 200 times a second. 1 Mississippi. Yeah, like about. We can actually probably know exactly what the clock rate is. But for now, oh yeah, let's try to look into that. So let's say monotonic timer or monotonic system time value, and here we'll say increment tick in device in interrupt. We've done that. And the next thing we need to do is we need to see set frequency of tick. And I think somewhere here in the RTC stuff, I saw something about changing the rate here. Right, changing interrupt rate, which is this guy. And the rate must be the lower 4 bits of register A is the divider's value. The default setting is 0, 1, 1, 0B, or 6. The value must be between 1 to 15. Dude, am I like crazy that this, like, where is this information coming from? I feel like I'm losing my mind. I really just want to look at the original datasheet. So like, what is the like chip, RTC chip name QEMU? Like, what am I emulating here? RTC. It's not helpful. RTC. Yeah, I don't understand. Maybe in like the QEMU source code, they'll tell me. So can we just like clone this guy really quick? We'll say git clone depth 1 of QEMU source. Hopefully it's not so large this will take a long time. Give it a sec, give it a sec. There we go. And if we look in here, do they have like an RTC? They do. Okay. RTC configuration. This doesn't say like what they're emulating. Git blame. Git blame. Why isn't this? How do I open up like the commit here? I guess we just go like this. Git show this. Merge pull request. Great. Great. Maybe I needed the... No, okay, I don't know. That's frustrating, but we can at least see here from... We can probably find what this is doing. And I wonder if this is just like propagating to the parent. RTC reference, QEMU clock time. Okay, so where's like the like configure RTC? Oh, there's many RTCs in here. Oh no. Okay, let's find dot dash iname star RTC.c. Hardware RTC. So how do I know which one of these is being used? Hardware RTC. Ah, okay. So probably somewhere i386 tells me which one they're using. This is crazy. How am I supposed to figure this out? Okay. So kconfig. Is there something like qemu i386? Like somewhere they must define which RTC they want to use for i386. Config i386. So probably there's like some sort of like default options that are used with i386. i386. Machine target. Oh my gosh, this is so painful. RTC driver and x86 PCs. Yeah, okay, so they have this like dev RTC interface, but I want to know like what the RTC is commonly reviewed somewhere around general purpose NVMe, e.g. DS, blah blah blah. Examples. Historic. Like, how am I supposed to know? I'm gonna like double check this Intel manual again and see if I missed something in it. So, system architecture. Do they have like an RTC in a diagram somewhere? Paging. Where do they say like IO setup? Task management. Virtual machines. I don't see anything about like IO in here. Which does make sense. It's like, why would this be on the CPU? It's not on the CPU. It's on the motherboard. I'm struggling. Software-based RTCs, radio-based RTC. Examples, the integrated circuits manufactured to make RTC, including blah, blah, blah. The RTC was introduced to PCs by PC18 1994. Here we go. Used a Motorola. Later, Dallas Semiconductor made compatible RTCs. Oh, there we go. This is what I was looking for. Okay. Okay. Ha ha ha! Here we go. This is exactly what I wanted this whole time. Okay. So somewhere he's gonna tell me what the registers are, and why was I got lost? Oh, right. And so here I wanted to see like what is the frequency divider. Right. So divider control is here. Registers. Okay. So let's look at the registers. Try to find the divider control, and from there we will be able to figure out what these values mean. Interrupt rate and square wave. So select register bits. Time base. Oh, periodic interrupt rate and square wave output frequency. This is it. Okay. So if okay, yeah. This is what we want. And so we can just, these are the frequencies. And so we can say that if we're at frequency divider 1, we're at 256 hertz, which is really all we wanted to know. So let's, here, we'll link this chip name here. And RTC, and here we can say that we want to configure the clock. So we'll just say, or configure the interrupt speed. So we'll say function set interrupt rate. And this will take in the ports like this. And here we'll say see docs for rate control, set up 256 hertz. And now we just read register A, which is easy. This is read CMOS reg ports, NMI enable, and register is A, which I don't remember like where the address is for these. Are these defined by this guy? Or are they determined somewhere else? Accessing CMOS registers. So where's like the register map? Register A. Here, okay. 0xOA is register A. So 0xOA for register A. And then we set the lower 4 bits. So data equals so first we like disable all of those. And so this is the lower 4 bits. So we set the higher, we say clear all the lower 4 bits. And then mask back in 1 to say 256. And then we write CMOS reg ports NMI enable register A data. And now we run this again. And 1 Mississippi, 2 Mississippi, 3 Mississippi. So how do I tell if this is right? Oh, it's not right. Because I haven't actually called this. So it's like set interrupt rate ports. Like this. 1 Mississippi, 2 Mississippi, 3 Mississippi, 4. It does seem to be going at the same rate, which is interesting. Let's try lowering the rate and see if that helps. Yeah, that's definitely lower, right? So, how can we determine if this is 256 hertz? We wait 1 second, and we should see it increment 256 times, which is what we're seeing. That is what we're seeing. We're seeing about 200 increments per second. Sweet, 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 sweet. Okay. So now we know that we're getting a 256 hertz clock. We know that the tick is incrementing once every 256. And maybe now we can implement some form of like sleep that happens based off of the monotonic clock. So if I run cargo run right now, which is like launching the VM, if I look here, we're using like maximum CPU, right? It's like railing one as hard as it can. But I think that if I say core is what is it? Arch ASM halt HLT. I think that this is still doing the exact same thing, but now since I'm like stopping the CPU until the next interrupt, we don't even see it show up on. Oh, it's here, 25%, which is a lot better. And I'll bet you it's even better if we disable these. Oops. What the heck? Why is this not working anymore? Oh, it's of course it's not working because I disabled the logger. I'm an idiot. So let's just double check that this is still working as expected. And if I disable this now, %. Yeah, so not awful. So let's now take a look and see if we can like implement a sleep function that's kind of like based around this. So we could say let's think about this. Our sleep function, I guess, can live in the RTC for now because the RTC controls time. That's not really like that great, but it's fine. So let's add on the RTC, make a new function sleep. And this is wrong. This is like an RTC driver, and adding sleep to that doesn't make sense. So instead what we should do is we should pass the RTC into a sleep function. So let's just leave this in main for now because I don't know where I want it to live. And we will take in the RTC, which is RTC. And we'll call RTC get tick. And this is a 256 hertz clock. And we also want to take in like a time. So we'll take in like time in seconds. Time S. So we'll say the start is this. And while RTC get tick is less than start, we'll say end is start plus time in seconds times 256. There's 256 ticks per second as U size, like this. That's the end, and we'll say while the current time is less than the end, we halt. So core arch ASM halt. And the idea is this will automatically wake up every time the CPU, every time an interrupt comes in, this will like undo itself. And so we should be able to say info sleep for 3 seconds, and we call sleep 3.0, and we pass in the RTC. And now exit halt. Probably here we need to service the logger, or else this won't make sense. And here we call IO exit. So we see 1, 2, 3, exit. Very nice. And we need to service the logger here too. Sleep for 3 seconds. And now we exit halt. That's so sick. That's sick. Let's go. Yeah, I'm pretty happy with that. I'm happy. Yeah. I think I'll call it here for today. I wanted to do a short stream. And yeah. If you want to see more, you can catch up on YouTube or catch me live at around 2 PST most days. I'll be skipping tomorrow, but yeah, most days I'll be live. Today we handled RTC and interrupt driver handling. So we set up passing the RTC registers into like the RTC interrupt handler, and we handled putting the RTC interrupt, or we handled like resetting external hardware interrupts, etc. We can now like we've proven the concept that like drivers can register interrupt handlers and work with them appropriately. So yeah, overall, this is just working nicely. Yeah, I think probably next up, I think it would be cool now. We're in a state now where the logger now, like I need to call this like logger service periodically to make sure that like logs get flushed. It would be nice to be able to have this like sleep be more like an async operation. And I kind of like the idea of like trying to implement async IO into this kernel. So that's probably what we'll be working on next time. And if you want to see that, you can catch me live on YouTube. Thanks for watching. See you next time. Bye.